Now we can move on to convolutional sequence-to-sequence learning. Okay, this is an assignment for you to watch that video. This is the architecture. I'm going to give you a quick overview, and then later on you can ask your questions. What are we doing? The architecture is going to be encoder-decoder type of architecture with some attention, because we saw attention is important. But then you are replacing RNNs and LSTMs with convolutional neural networks. For the encoder part, you have your sequence of inputs, which is basically a sequence of integers. You're going to use your word embeddings to turn them into vectors. You're going to have some positional embeddings. This is really important because it matters. Are you translating the first word? Are you translating the second word in your sentence? And convolutions are going to lose that ordering to some extent. Basically, you're going to lose the ordering in a local manner. Any word within the window that your convolution is looking at, you can just switch the role and nothing happens. That's why you're going to introduce these position embeddings. And the way that you're going to do it, these E's could be either learnable or they could be deterministic based on sines and cosines. So this idea is powerful. We're going to see that when it comes to transformers again. The rest of it is convolution. And we know that convolutions have that local window of field of view, or we can call it receptive field. Then later on, you're going to have a fancy activation, which is basically you divide your vectors into two portions. One part of it you're going to push through sigmoid. The other part you're just going to multiply pointwise. As your activation, you're going to end up with some encoded sentence, encoded input sentence. Decoder is very similar. You're going to end up with an encoded version of your output sentence. But there's a catch here. When it comes to the output sentence, you're actually interested in predicting the next word. So you are not allowed to put that as an input to your architecture. And therefore, you're going to have one-sided convolutions. And now it's time for your output of your decoder to pay attention to your encoder. And the way that you're going to do it is using dot products and then pushing those dot products through softmax because you have an attention budget of 1. And then you sum them up. You're going to end up with a bunch of vectors that you can use to output the translation. So all we did was replace RNNs with convolutions. For input, we were allowed to look forward and backward. For the output sentence, the translated sentence, you are not allowed to look forward. That's the only change. The rest of it is attention, which is a linear combination of your input vectors. And the coefficients for that linear combination, they have to add up to 1. So you're just going to use softmax to make that happen. And then this architecture is much simpler than Google's neural machine translation system. And it's giving you better performance when it comes to English to French, English to German, and English to Romanian. And it's extremely easy to implement this. I think it's a good time for me to stop. For those of you who have questions, I'll be around. For those of you who want to leave, we can leave.